Welcome to today's topic. Today we are going to discuss the topic order of a reaction. It is continuation to our previous kinetics of chemical kinetics, that is rate of a reaction. Then next one is order of a reaction. What do you mean by order of a reaction? That is, in chemical kinetics, the reactions are generally classified in terms of their order. Order of a reaction is defined as the sum of powers to which the concentration terms raised in the rate law expression. For example, consider the rate expression, that is R is equal to K into Ca. The power of this one Ca stands for the concentration of the reactant, and this power of this term Ca is raised to 1. So hence the order of this particular reaction is 1. So this reaction is a first order reaction. If K is R rate constant, R is equal rate of a reaction, R is equal to K into Ca square, or here K is equal to Ca into Cp. Here Ca square, so concentration power of this concentration term is 2. Here the sum of the Ca is concentration Ca raised to 1, Cb raised to 1. So the sum of this one plus 1 is equal to 2. So this one is follows second. All the equation is a second order reaction. Another case, R is equal to say Ca raised to 3, or in the R is equal to K, Ca into Cb into Cc, Ca raised to 1, Kb raised to 1, Cc raised to 1, or K is equal to R is equal to K into Ca square into Cb 2 plus 1. And this one, all this equation is for the sum of the powers is equal to 3. So this one is a third order kinetics. Suppose a reaction of this type A plus BB gives product, and the rate of a reaction, which is R is equal to K into Ca. This reaction is a first order reaction. So this order of a reaction is an experimental quantity. Here what it follows, the rate of reaction is R is equal to K into Ca. So this follows a first order reaction from the rate law. So the order of a reaction is purely an experimental quantity. Then next, how you can express different rate equation or rate constant for a zero order, first order, second order, and third order reaction. First, we calculate a zero order reaction. In zero order reaction, the sum of powers is equal to 0. So we can write it there. R is equal to K0 into Ca raised to 0. So the order equal to 0. So this equation K0. So the rate that is independent of the concentration, or the rate of a zero order reaction is a constant. It is equal to K0. Many photochemical reactions follows the zero order reaction. For example, photochemical reaction of hydrogen and chlorine, that follows zero order reaction. Next is a first order reaction. Consider a reaction that is A gives B, and the first order reaction, the rate is equal to R dx by dt is equal to minus dCA by dt, that is equal to K1 into Ca. That is the rate equation for a first order reaction, where Ca is the concentration of the reactant A at the time of rate determining reaction, and K1 is the rate constant or velocity constant for a first order reaction. Then simply we are used to find the rate constant equation for the rate constant. So simply rearranging this equation, we get this time minus dCA by dt is equal to K1 Ca. Rearranging, we get minus dCA by Ca is equal to K1 into dt. That is equation number 2. If C0 is the initial concentration at the time t equal to 0, we take C0 is the initial concentration and C is the concentration at any time t. Then we integrating this equation 2, we get integrating equation C0 to C. Integrating equation minus integrating C0 to C, my dCA by C is equal to integrating t is equal to 0 to t K1 into dt. This equation minus ln C by C0. is equal to K1 into T. Rearranging ln C0 by C is equal to K1 into T, and we get T K1 is equal to 1 by T ln C0 by C. This is the first order rate equation, and rate constant K1 is known as first order rate constant. So you can usually written as in the form of another form. If A is the initial concentration, and after some time X moles of reaction undergo reaction, that is at time T, then the concentration of the reactant at the time T is equal to A minus X, that is initial concentration minus at the time of T. Then what happened? In such cases, C0 is equal to initial concentration A, and C become A minus X. Then substituting, instead of C0 and C, substituting A and A minus X in equation 3, we get K1 is equal to rate constant for first order reaction, or first order rate constant is equal to 1 by T into ln M by A minus X. That is, the concentration of the reactant decreases and that the product increases for a first order reaction. If we plot a graph, that is C against time, the reactant time increasing concentration decreases, and that of the product increases exponentially. Say concentration versus time plot for a first order reaction. And to find the units of a reaction, that simply we can 1 by Ca by dCa by T. These two terms, Ca and dCa, is a concentration term. So this one, mole decimeter ratio minus 3, mole decimeter ratio, and dt is the change in time, that is in seconds. This one is cancelled. So K1 rate constant for a first order rate constant is equal to second raised to minus 1. That is the unit for a first order rate constant. And this one, decomposition of hydrogen peroxide in aqueous solution and decomposition of ammonium nitrate in aqueous solution are the examples for a first order reaction. That is order of a reaction, zero order and first order, and rate constant for a first order reaction. Hope you understood. Thank you.